Okay, so let's draw a picture here. So x to the 2/3. You're going from y. So does that hit the origin? It does. So it does hit the origin. That's nice. X to the 2/3 is always going to be what? Positive or negative? It's always going to be positive. And is it going to be concave up or concave down? So it kind of looks like this. Is that correct? Y equals x to the 2/3. And you're going to go to x equals 1. So let's go to x equals 1. So a different color here. What's 1 to the 2/3? So it's going to intersect where? Exactly. So like this, and y equals 0. So what are we rotating? We're taking this right here and rotating around the y-axis. So after you draw that one side, what else do you draw? What else do you draw? The same thing in the other side. You draw the reflection. So you have this. Let's do change colors again. You know, that my steepness isn't too good right there. Well, the relative curvature is the best. But here's the reflection right here. Here's the reflection. And then what do you draw once you have the reflection? You draw one of the what? Someone already said it. One of the what? One of the washers, someone says. One of the discs. What's the challenge here? The challenge here is that there's a hole that's punched out of the middle here, right? So here's one of your washers right there. There it is. Start with a... We're integrating with respect to not x, y. Where's the little thickness? This washer is perpendicular to the y-axis. Its infinitesimally small thickness is a part of the y-axis. So you're integrating with respect to y, integrating with respect to y. And what goes on the front? What's the constant that's out front? Pi. And it's going to be the biggest radius squared minus the little radius squared. And what's our lower limit of integration? 0, and it goes to 1, because we're going from 0 to 1. That's your scanning from left to right. 0.
Wait, we're not going from
Oh, excuse me. Wrong arrow, sorry. So you're going from 0 to 1 like that. You're going from 0 to 1. So now you need to write big R in terms of y. Well, the big radius is always going to be what on this one? Nope. The big radius is always going to be, someone said it, it's just 1. What's the big radius is right here. That's this distance right here. Does that change at any point when you go from 0 on the y all the way up? No, it stays constant. The little radius is this function right here. The little radius is this function, but you need it in terms of y. So this thing is the same as what? X equals y to the 3/2. So it's going to be minus y to the 3 over 2 squared dy. So what do you end up with? Pi 0 to 1 of 1 minus y to the 3rd dy. There it is. And is that something you can integrate? Yes. At this point, the challenge is the setup. At this point, the challenge is the setup. The integration is not the challenge. It will get more fun when we have things that are pretty, a little bit more involved, but this is the challenge right now. Good. So you're rotating, it's going to be a similar rotation, but it's moved over a little bit. So first of all, you have y equals x. Does that go through the origin? It does. So we have y equals x right here, going off like there. And then you have y equals 0. So you have y equals 0 right here. And you have x equals 2. So let's just say that's, I don't know, right here. I can't change the orientation of the thickness. Anyway, that means x equals 2, and then you're also, well, let's make that x equals, excuse me, let's make that one x equals 4, just so we don't have to go anything for it. X equals 4. And then let's go with x equals 2 right here. Right there. Yay, exciting. So what's the enclosed shape? It's this right here. The enclosed shape, everybody, is right there. There's your enclosed shape. That's what's enclosed by those 4 boundaries. And what are you rotating it around? X equals 1. So you draw x equals 1 in. X equals 1 will be right here. And then after you draw your x equals 1 in, what should you then draw? The reflection, right? Draw the reflection. So we know it's going to start, it's going to be here down to here, right? And it goes back a couple, and then it goes up the same amount. Like that. There's your reflection. Did I do okay there? It's not bad. Now draw one of your slices. Let's draw one of the slices. So in this case it's washers. So let's draw one lower down first. So if we do one lower down, we end up here. Here's your slice. Look at this. You kind of see the slice, everybody? So what is this going to be with respect to x or y? Y. It's perpendicular to the y-axis, so it's going to be with respect to y. What's the lowest y can be? What's the lowest? It goes from 0 all the way up to what? What's this point right there? It goes to 4, and there's a pi outside, and it's big R squared minus little r squared dy. Now, everybody sees the washer where it's at? What happens as I move it up? What happens eventually? What changes? Little r changes. Little r changes. At first, little r and big R are the same. At first, here's little r right here. And here's big R. What happens once you get higher than here? What happens when you get higher than here? The little radius changes, but the big radius stays the same. So how many integrals are we going to need to use? 2 of them. The first one is going to be pi from 0 to what? It goes from 0 to 2 of big R squared minus little r squared dy. And we're going to add together, yes, I'm sure, we're going to add together what? 2 to 4. 2 to 4, yeah. 2 to 4, yeah, there's a pi outside, thank you. 2 to 4 of, we'll call this r, the little r1, and the second radius right there. That just means the second radius, because there's going to be a second function in there. At first, what's the little radius? At first, what's the little radius? At first, it's definitely 1. It doesn't change, right? And what's the big radius the entire time? No, it's 3, because you're going from 1 to 4. What's the big radius the whole time? 3, exactly. Now, the only one that's a little bit tricky is this little r2 right here. We have a function x equals y, so what is the actual radius going to be? Well, we want it in terms of y, so what is it going to be? It's dy, so what is it going to be? Y. So all you have for your integral is pi 0 to 2 of 9 minus 1 dy plus pi times 2 to 4 of 9 minus y squared dy. And this one is just pi times 0 to 2 of 8 dy. There's no y in it. Plus this, 2 to 4 of 9 minus y squared dy. Now, is this something you guys could integrate? Yeah. The only thing you have to be careful of here, 2 things. 1, how many integrals do you need? 2. And you're not rotating around the y-axis, so it's not going from 0 to 4, but for the big radius, it's going from 1 to 4. So the big radius is 3 the entire time. For the first half, it's just 1, and then it changes. When the bounds change, you need to write a different integral. If we just went from 0 to 4 and we didn't change it, we would be adding in all of this in the area in the corner here. Like if we added this in right there, that's what we would get. We get a cylinder with the hole punched out, but that's not what this is. That's not what this is. So we have the line y equals x right here, and then we have y equals x squared right there. So then we have that region rotated. That's good. And it's good, you know, do you see what happens when you don't put that line and you kind of lose perspective a little bit? If you put both of them in, you can kind of get, now do you see the disc right here? Yeah. A little easier to see with that hole in it.
So the center of the hole.
So there's a missing hole there. So that thing gets, it's like a funnel that's bent kind of in a way. That's exactly what we're talking about.
The center of it is that
it's y equals 0. It's rotating around y equals 0, which is the x-axis.
Point is it 0, 1? I mean,
what?
1, 0.
Where they intersect? They intersect at 1, 1. They intersect at 1,
no,
comma 1.
The middle of the washer.
The middle of the washer is centered around y equals 0.
Yeah, but the point.
What point?
No, the coordinate. Any point. It doesn't matter. It's an infinite number.
I don't understand what's going on. We're integrated with respect to x. So you have pi. What's the lowest x value? Left is 0, and then it goes to what? Why do we know it goes to 1? They intersect at 1, 1. So you have dx, that's good. And in this case, what's our bigger radius going to be? What's the bigger radius? Just x. Because you're going from 0 all the way up to the function. What is the function? Y equals x. And what are you going to subtract from it? What's the lower function? X squared squared. There it is, right there. Right there. So this right here is your inner radius right here, kids. This right here is your inner radius. What distance are we talking about? We're talking about the distance from there to there, from 0 to the function. What is the function? The function is x squared. And from 0 to 1, x squared is less than 1. So you subtract it. So what do you end up with? You end up with a relatively straightforward integral. Pi 0 to 1 of x squared minus x to the dx. Yes, you have something, Keaton? So the thing you want to avoid is, it seems logical that this should be 45 degrees, at least for perspective. Don't make it 45 degrees. Make it 30, and it'll be a lot easier to see the three-dimensionality. I totally see what you're drawing there, but yeah. So you have your two sides there. Yep. This is fine. I see the disk. It's great. Okay, so are we integrating with respect to x or y? Y. It's definitely going to be y, because this little slice right here, you see that right there? That slice, it's a little piece of the thickness. The thin part of it is going to be part of the y-axis. You also can think about it like this. With washers, if the washers, whatever axis it's perpendicular to is what you're integrating with respect to. If revolving around, if it x, so you're revolving around the y-axis, so it's perpendicular.
So if you're revolving around the x equals point,
you're around something parallel, so it's going to be, generally speaking, yes. But here, once again, Alex and Keaton, the key thing is this. Don't break it down like that. Break it down like this. Draw one of the slices, and then ask yourself, what is it perpendicular to? Do it like that. What's the lowest limit of its integration right here? 0, and then it goes all the way up to what? Goes up to, yeah, what's the intersection point right there? Goes to 1, right? Now here's the deal. You have to be careful about this. So you have the big radius, and then you have the little radius. Which one's a little easier to describe, the inner or the outer? I would say the inner radius is easier, because this is the inner radius right there. And what's that line? Y equals x, right? So you have minus what squared? Minus, no, because you want it in terms of y, so what is it? Y squared, because it's x equals y. It would be a little different if it would equal something else. And then the outer function, you know, is y equals x squared, but you need it, so x equals the square root of y, so it's the square root of y squared. So you end up integrating 0 to 1 of y minus y squared dy. Theoretically, do you come up with the same thing? What you actually will come up with the same thing, sure. Okay.